Okay, so I'm going to put the whiteboard up and give, not that whiteboard, give a brief overview of what we are focused on today. So today we're focused on mainly two things. We have the net force equals ma, which when we translate that into rotational language is net torque equals I alpha. I could tell from the contest that most of you are getting a pretty good handle on how to compute torque. So today we'll be doing problems where alpha is not zero. So they will not be static equilibrium, and we'll see how we go about that. And then the second one is using kinetic energy, which in linear physics is 1/2 mv squared, and in rotational language that's 1/2 I, let me write it as KE rotational, is 1/2 I omega squared. So the first one, we always just called it kinetic energy. Now we call it translational kinetic energy. And the second one, when things are rotating, we have rotational kinetic energy. And we're going to see today how those two guys are interrelated. And that should help you with the lab that, was going to be due today, but I decided to make it due tomorrow so that I could kind of explain some of the physics behind it. So let's talk about that lab example. We're going to imagine we have a ramp with a height of, let's say, 1 meter. And on the ramp, we put a ball. Okay, so a solid sphere. It could be an apple. Apple's probably not that round, so maybe an orange or a cantaloupe or something. And we're going to just let it go. And at the bottom, it's going to be moving with some final velocity. And that's what we want to know. So we've done problems like this before. We would say the net work equals change in energy. To find out if there is work, we would be asking about the external forces. And this is kind of subtle. When something rolls down a ramp, we say if it rolls without slipping. Okay, so what does that mean? Technically, it means that there is friction. Okay, there's friction. As this thing rolls down, there's going to be some friction, and that's why it rolls instead of slides. Or maybe kind of point this back up the ramp. But it is static friction because it's not slipping. If it's slipping, then we have kinetic friction. So static friction doesn't do work because the surface, the part of the surface that's in contact, does not move. And that's hard to visualize. You kind of have to sort of almost zoom in with a microscope. What you see is when you have a rolling object, it becomes a little bit flat on the bottom. And then what happens is this end kind of lifts up and this end kind of moves down. But the part that's in contact, I'll color that with different color. The part that's in contact is just in static contact. So all the the importance of that is to say that even though there's friction, there's no work done as long as we roll without slipping. Additionally, if we roll without slipping, then we could say that delta x, the distance it travels, would be r times delta theta, or v is r times omega, and so forth, where r would be the radius of the object. A equals r alpha. These are true as definitions of what omega and alpha and delta theta mean for something that just spins in place. But additionally, if we have something that's moving both in an angular setting and a linear setting, so it's rotating with an omega and moving with velocity v, those two variables don't necessarily have to be connected. Just imagine you're in the car, and you get in the car in the winter, it's icy outside, you hit the gas, and the wheels could spin without the car going anywhere. So it's possible that there's an omega but no v. But if we have rolls without slipping, then whenever we have omega, we have v, and they're related by this relationship. Okay, so those are the two fine points that we need to be aware of. But those are going to be the case for all of our rolling problems. So it's always going to be rolling without slipping, and so therefore we will always have no work done by friction, and these relationships between the linear and rotational variables will hold. Okay, so that was a lot of talking. How do we solve this problem? So the change in energy, ordinarily in our old problems it would have split into delta Ke plus delta Pe for gravity. But we have two kinds of Ke now. So it has to split into translational kinetic energy change and rotational kinetic energy change. Because those, in principle, could both change. And if it rolls without slipping, they will both change. Okay, so I need to just modify my page here a little bit. And we're going to move on to the next page. So we have 0 equals Ke translational. Let's use a T. Let's be very careful about our notation. KET final minus KET initial plus KER final minus KER initial plus PE. I'm just going to write PE final and PE initial. I'm not going to worry about putting a G on there because there's no spring, so there's no ambiguity what kind of potential energy we're talking about. So because it starts from rest, its translational kinetic energy is 0, but so is its rotational kinetic energy. It's just not, it's not moving. If we go back to the picture, it has potential energy at the top, but it has none at the end. So the initial potential energy is there, but the final potential energy is gone. So we can additionally cross that out. And then what we get is just that the initial potential energy is equal to the sum of the translational final kinetic energy and the rotational final kinetic energy. So in words, in concepts, what would we say? Say that in this problem, you start off with some potential energy. As it rolls down, it loses that potential energy. Where does it go? It now gets split between kinetic translational and kinetic rotational energy. So if we have that concept in mind, we could probably just start from right here. So our initial potential energy would be mg times that initial height h, and the final translational kinetic energy is just 1/2 m the final squared, and the final rotational kinetic energy is 1/2 I omega final squared. So all I'm doing is conceptually thinking about the problem right now and putting in place the formulas for each thing, but I'm not really doing any math yet. I'm just kind of getting the right terms in my equation to work with. Now here's where we have to know things. So for the first term and the second term, we already know how to work with them. But on this next piece, we have to know what to do with the moment of inertia. Let's kind of make a long arrow there. Also, what to do with omega final. So for omega, we know that V final equals R times omega final. That's because of this boxed equation here relating V and omega. And so, therefore, omega final would just be V final over the radius. I'm going to use capital R's here for the radius, in part because my V's and R's look a little similar, and also because I'm using a little r for rotational. But no real difference in meaning between big R and little r. So that's omega final is actually related to V final, and we can substitute it in a minute. How about the moment of inertia? So for the moment of inertia, we have to go back and look at the table. So last class gave you sort of a list of moments of inertia of different shapes, and at the front of the chapter, the problem book chapter, I think it's in the college physics book, there's a table. But in one of those books, at the beginning of the chapter, there's a table. So since we know it's a solid sphere, we look up the I formula for a solid sphere, and it turns out to be 2/5 m r squared. Okay? So I can just put all of that information into my equation. So in place of the moment of inertia, we just put 2/5 m r squared. And in place of omega final, we put V final over R, and then we square it. So what's going to happen is that because we have an R that gets squared in the denominator, and we have an R squared up top, those guys just cancel. Additionally, our mass now cancels because the moment of inertia is related to the mass. So what we have left after those cancellations is GH equals 1/2 V final squared plus 1/2 times 2/5 times V final squared. Doing a little algebra, we might multiply both sides by 2. And then we have just V final squared plus 2/5 V final squared, or we could factor out the V final squared and have just 1 plus 2/5. And finally, then V final squared is 2GH over 1 plus 2/5. And this means that V final is the square root of 2GH over 1 plus 2/5. Now notice, when we solved this kind of problem before, hopefully you remember that we would have had just as VF equals the square root of 2GH. And we could have thought of that as divided by 1, but there was no 2/5 there. So what has happened by introducing the rolling motion is this ball, it doesn't just slide down the ramp, in which case there would be no 2/5. It rolls, and because it rolls, some of the energy goes into rolling motion, and there's less left over for the translational kinetic energy. So when we put in our numbers for this problem, let's see, we had a height of 1 meter, and, well, that's it, right? It's the only number we need. 2 times 9.8 times 1 over 1 plus 2/5. And I get 3.74 meters per second. Whereas we've gotten 4.43 meters per second without rolling motion. So we did this example. One of our first examples of conservation of energy was a block sliding down a frictionless ramp from a height of 1 meter. And that's the velocity that we got. Okay, so any questions? All right, well, how does this relate to your lab? So if we look at what happened here, it's the 2/5 that is special, that's different, that's new. It's coming ultimately from this moment of inertia. And so if we did this problem over, but in a generic way, where we don't know what kind of object we have, we would have, instead of a 2/5 mr squared, we would have just some constant c that would depend on the shape. And what ultimately we get out of that, if we do that process, is we would have 2gh over 1 plus, instead of the 2/5, it would just be a constant c. And see then, by analyzing this equation, that the bigger the constant c is, since it's in the denominator, divide by a bigger number, we get a smaller number. So the bigger the constant c is, the smaller the final velocity should be. So when we're having a race between a ring, a cylinder, a hollow sphere, and a solid sphere, to determine who should win, all we have to do is look at the table, which I provided last time, which you can look up, and see the varying c value. And this should tell you, in principle, which one is the fastest, the second fastest, the third fastest, fourth fastest. And that's the first part of the lab, is to just make those comparisons. I think that's the first part. The other part of the lab is to try rolling 2 of the same object but different sizes. And the point of that is to confirm that the radius of the object is irrelevant. It just cancels out. And the mass of the object as well just cancels out. So if I roll, a large sphere and a small sphere together, they should basically have the same velocity when they get to the bottom of the ramp, assuming everything else is equal, like how I released them and that they roll without slipping and those things. Okay? Any questions? Okay, so you can use, without proving it, in your lab, you can use this equation to get, a theoretical idea of what the final velocity is going to look like by looking up the shape, finding c, and measuring the height h. So we're going to just go ahead and go forward and do some more problem solving, just for practice, but you want to keep all this stuff in mind when you are doing your lab calculations tonight. Okay. So I want to do kind of the flip side of this calculation. Suppose we have, I want to make it level. Okay, suppose we have just a flat level surface, and then it starts to go uphill. And we have an object. Let's say it is just a hula hoop. So that's a ring. And it's moving with an initial velocity of, let's say, 5 meters per second. And I want to know how high is it going to go if it rolls without slipping. So we start out the same way. Network equals change in the energy. If it rolls without slipping, we don't have any work. So we're going to have delta E translational plus delta KE rotational plus delta PE for gravity because it goes uphill. And all of those are going to change because at the end it's going to stop. That's how we know we're at the highest point. So we will have KET final minus KET initial plus KER final minus KER initial plus PE final minus PE initial. Then we go through these one by one and we say, well, does it have final energy of translation? No, because it stops. Did it have initial kinetic energy of translation? Yes, it was moving 5 meters per second. How about final rotational kinetic energy? No, because it stops. How about initial rotational kinetic energy? Well, if it's going 5 meters per second and rolling without slipping, then if it moves, it must spin. So it has that. How about final potential energy? Yes. What about initial potential energy? No, because we will just choose to call this y equals 0. Okay, and we are this time trying to solve for h. So we're going to keep the potential energy on one side and move the kinetic energies to the other side. So notice I moved the kinetic energies to the opposite side. They had negative signs, so they become positive. We then have m times g times h equals 1/2 m the initial squared plus 1/2 I omega initial squared. And here's where we have to put in, we know about moment of inertia, so we have to look it up for a ring. And if we look it up for a ring, the value is just 1 times mr squared. So the constant c, that constant is just 1. Just writing the 1 in there so you can kind of remember that. And then the initial omega would be v initial over r, and then we square it. So every time we do this, mixing linear or translational kinetic energy and rotational kinetic energy, these r's are going to just cancel. And now, because each term has a mass, the m's cancel. So finally, g, I just divide both sides by h. I have 1/2 v initial squared plus 1/2 v initial squared over h. That's just v initial squared, sorry, over, I'm not solving for g, I'm solving for dividing both sides by g to solve for h. Sorry about that. So we get 5 squared over 9.8. That's going to be 2.55 meters. And now, again, to just make a comparison between this and what we would have done if we didn't have rolling motion. If we didn't have rolling motion, we wouldn't have this. And so we would have had a 1/2 still in this equation, and it would only go half as high. So if something rolls down a ramp, it's going to go slower than if it just slid down the ramp with no friction, or even possibly with some friction. It'll be slower. On the other hand, once something is rolling, it has a lot of energy stored in that rolling motion. And so in this case, half of the energy is stored in translational kinetic energy and half of it is stored in the rotational kinetic energy. So it wants to keep going much further. Okay, any questions? Okay, so that's how rolling motion works. And the other thing, you've got a couple of problems, maybe 2 or 3 of those to do tonight, and then your lab work. But the other thing we wanted to talk about was the Newton's second law when we have rotation. So just to give you an idea, suppose we have a merry-go-round. Okay, so you know merry-go-round, it's like a disc and kids sit on here and it spins, right? So suppose we want to take a merry-go-round and the mass of it is 50, actually they're pretty massive, let's say 100 kilograms. And we're going to just push it with a force of 50 newtons. And we want to find the angular acceleration. Okay, so we're probably going to apply that force at a right angle to the radius because we don't want to waste our effort, and we know a right angle is the best. So we're going to say at 90 degrees to the radius. And suppose the radius is 2 meters. So what we do is we look at all the force acting on the merry-go-round. The forces are, there's a normal force and a force of gravity, and then there is our applied force. And the normal force and force of gravity do not create any torque because they are at the center, they're at the pivot point. We don't get to choose a pivot point anymore. There's already a pivot point sort of because it is actually rotating about a certain point. So when we try to sum the torques, we would have torque normal and torque G and torque from the applied force. But instead of equaling 0, they equal I alpha. But as we discussed a moment ago, the torque from the normal force and from gravity are 0. So we only have the torque from the applied force, and that's going to be R applied, F applied, sine of theta applied. And then the moment of inertia. Well, we have to think what shape this is most like. Who wants to throw out a guess? What shape, if you were to just describe the merry-go-round with the closest shape you could find, what would you pick? Is it a sphere? Is it a cylinder? Is it a ring? Is it a long straight rod? What is it? Ziad?
A ring?
It is more like a ring than it is like a sphere, but I think there's a ring would then have to be hollow in the middle. So ring would really just only have a rim on the outer edge, but this is solid all the way through. So what do we call that shape? Haley?
cylinder?
I can't hear you if you're talking.
Oh. Is it a cylinder?
Yeah, it's a cylinder or a disc. Those are kind of the same thing. So we would go to our table and we would look up the formula for moment of inertia of a cylinder or a disc. And the formula for that is 1/2 mr squared. And we still have alpha. So the radius is just r, the big R, the radius of the disk. That's the R for the torque formula, because that's where we apply the force. We hold on to the edge of the merry-go-round. So we have R times F applied sine of 90 degrees equals 1/2 mr squared alpha. You can see one of those R's cancels out. And then we do algebra. To solve for the alpha. So it's going to be 2 times F applied over mr, keeping in mind, that sine of 90 is 1. So alpha then would be 2 times 50 newtons over 100 kilograms times 2 meters. So those 2's just cancel out, and we get 1/2, and our units should be radians per second squared. Okay, so solving a problem that involves net torque, if it's not net torque equals 0, it still follows a lot of the same procedure. We have to draw the force, we have to figure out, we don't have to choose a pivot point because it's chosen for us. And usually, because it's chosen, certain forces create no torque about that pivot point. Usually whatever's supporting the object doesn't create a torque. And then we see what's left, but instead of 0 on the right-hand side, we have I times alpha. Haley, question?
Yeah, I was just wondering, so the only time that we mix the linear and the rotational forms is if it says something about rolling without slipping. Is that correct?
No, because we're going to see an example here where we have forces and torques. And in fact, our next example, we'll see also, again, mixing the linear and rotational forms. Okay. Any other questions about this example? Okay, so let's do exactly what Haley is asking about. Suppose we have a pulley, and from the pulley we hang a couple of objects. Okay, so maybe we have an M1 and an M2. Maybe M1 equals 10 kilograms and M2 equals only 5 kilograms. And we want to find the acceleration of the masses. But now our pulley is a big, heavy pulley, and it has a mass, let's say its mass is 3 kilograms. So when we did this kind of problem before, there would be fine print that said, assume that the pulley is massless and frictionless. And what that meant was that the tension between M1 and M2 kind of ignores the pulley. And so it's not a force between M1 and the pulley and a different force between M2 and the pulley, but it's just a force between M1 and M2. That's a perfectly fine approximation to make if our pulley is very low mass. But if it does have mass, just look at this for a minute. Imagine, we have a tension right there, So, and there would be a tension pulling down on the left side of the pulley. And on the right-hand side, if that tension is the same size, the pulley does not turn. So it actually has to be a little bit smaller on the right-hand side in order for the pulley to be able to rotate the opposite way. And what that means is that the tension in the two pieces of string is no longer the same. So we're going to have a T1 pulling up on the mass 1 and a T1 pulling down on the pulley, and then a T2 pulling down on the right-hand side of the pulley and pulling up on the mass 2. And we additionally need to have forces of gravity. So there's going to be a big force of gravity, 1, and then a small force of gravity 2. I mean, my scale's probably not great. Force of gravity 2 has to be smaller than the tension 2 so that mass 2 can go up. That's kind of why I drew it so small. Okay, so here's the situation where we have an object that rotates, the pulley, and objects that move in a straight line, and they're all kind of connected. So if we have a radius, let's just kind of draw the radius here. Radius r to the pulley, we can see that the tension is making a right angle to that radius. And it's going to make a right angle, you know, on both sides. So that will make our torques fairly easy to compute. So how do we solve this for the acceleration? Well, we use the same kind of tricks that we used for pulleys before. We want to be able to say that they all have this accelerate with the same sign, you know, that is they're accelerating in the positive direction. So we make a bending arrow. We say that's going to be the plus orientation. I would recommend making that bending arrow counterclockwise because we already have been using counterclockwise as positive for our torques. And so if we don't stick with that, we are likely to make a mistake somewhere. Then we just go through and we write down net force equals ma for each mass. So net force on mass 1 equals m1a, net force for mass 2 equals m2a, and now net torque on the pulley equals I pulley times alpha. So that's Newton's second law written for all three masses in my system. I only have to worry about the y direction for those two guys, fortunately, or I'd be running out of space. So what happens for mass 1? For mass 1, we have force of gravity 1 minus T1 equals m1a. So using my bending arrow, so down is positive for mass 1. For mass 2, using the bending arrow up is positive, so we're going to have T2 minus Fg2 equals m2a. So what happens with the torque? Let's do our torque down here. So we're going to have a torque 2 and a torque 1. We additionally, if we want to just be 100% accurate, we have acting on the pulley, a force of gravity for the pulley, and some kind of normal force for the pulley, whatever bracket is holding the pulley. But those guys don't create torque because they're located at radius equals 0. So I can draw them in, but cross them out. So according to my picture, the tension 1 is trying to make the pulley go counterclockwise, so it gets a positive sign on its torque. And tension 2 is trying to make the pulley go clockwise, so the torque for tension 2 should be negative. And I started to write equals 0 out of habit here, but this should be equal to I pulley times alpha. So the torque for tension 2 is going to be R times T2 times sine of 90. And for tension 1, it will be R times T1 sine of 90. Generally, a pulley is a disk, so I'll use the moment of inertia for a disk. Now, your problem will tell you the shape. It won't make you do guesswork, but that's typically what we'll see for a disk. So we'll have 1/2 mass of the pulley times radius squared, and then we can replace alpha with A over R, using those kind of master equations to convert between A and alpha, between our linear and rotational variables. So let's see what happens. This is going to be just a whirlwind of canceling. So the A over R, that R is going to cancel one of the R's in the moment of inertia. Sine of 90 is 1. And then we have 1 R left on each term. So the second R on the moment of inertia cancels against the R's that come in the torque equations. And so what we get is finally very simple. Minus T2 plus T1 equals 1/2 mass of the pulley times A. Okay, so now this brings us back to where we typically get with this kind of problem. We have our equations for each mass written down. We have 3 unknowns, T1, T2, and A, and we want to eliminate unknowns. Maybe we want to solve for all of them, T1, T2, and A. But generally, maybe most importantly, I want to find A. So how do I do it? Well, I usually, in the previous cases, I would just stack the equations and add them. So let's see what happens if I do that now. If we have T2 minus M2G equals M2A, and M1G minus T1 equals M1A. So instead of FG2 and FG1, I'm putting in formula M2G and M1G. And then we have minus T2 plus T1 equals 1/2 mass of the pulley times A. And we try to just add these equations. And like magic, it just goes away. The tension, that is. Not the coronavirus. The tension goes away like magic. And on the right-hand side, we have A on each term, so we're going to have A factored out and have just M1 plus M2 plus 1/2 mass of the pulley. On the left, all that's left is M1G minus M2G. So we can solve for A by just dividing. We'll have M1G minus M2G over M1 plus M2 plus 1/2 times the mass of the pulley. And if you would go back and compare with what we had in the past when we did this kind of example, you would see exactly the same thing, except we don't have this. We don't have the mass of the pulley. So if you would put the mass of the pulley in as 0, you would get that old result. And so let me just, on my calculator, plug in these numbers. I get 2.97 meters per second squared. Okay, and if we had ignored the mass of the pulley, just for curiosity's sake, it would have been 3.27. So even with a 3 kilogram pulley, we make only about 10% error to ignore the pulley. Okay, any questions? So just to kind of recap, this is another example where we do have linear and rotational physics kind of merging together. So if we have a system where part of the system rotates and it's connected to parts that move in a straight line, then for the parts that move in a straight line, we're using net force equals ma, and for the parts that rotate, we use net torque equals I alpha. But at the end, once we put in our torque formula and the formula for moment of inertia and the formula for alpha in terms of A, we can make it all look like linear equations. Or it's possible to go the other way and try to make everything look like rotational equations, but I tend to like this way better. Okay, so we're going to take a short break, and after the break, we will go into the textbook and pick a couple of problems there and work them just for practice. Okay? Any questions before we take a break? All right, so stopping recording.